Thank you so much, Anil. All right, so yeah, let's get started. Thanks very much for coming. I am going to be talking on the, if I understand correctly, the last virtual infinity seminar of the, let's say, the academic year, so to say. And I'm going to be talking about on a project I've been working on rather recently, although, sorry. Although actually it started quite a while ago. So I'm going to be talking, so restricting to spherical symmetry, I'm going to be talking on neutron star and black hole initial data on hyperboloidal slices. And well, my plan was to actually have the paper ready by now. Of course, life happens, and I guess we're all familiar with that. As you can see, I'm still hopeful that I get it out this month on the archive. Let's see. I think it's doable. But let's go to the topic. This work originated during my visit in 2023 to Kyoto University, where I was basically hosted by Kotaro Kyutoku. And we were thinking about stuff to work on. And one of the suggestions that Kotaro came up with was, let's try and do a hyperboloidal version of the work in this paper here, which is on the topic of Bondi accretion. So the idea is you have a neutron star, and you put a very small black hole at the center. So of course the black hole starts going to accrete the neutron star, and you can do this in spherical symmetry, which is far simpler from an implementation point of view. And that is something that as such should be relatively straightforward within still spherical symmetry, given that all what would be needed to extend the current what we have in spherical symmetry for the hyperboloidal evolutions would be to add the relativistic Euler equations for the hydrodynamical part, which again is not trivial, but this is something again relatively accessible as compared to other options. And indeed, the first thing that is needed is initial data. And I started to think, because how can we, all right, so the issue is already from the initial data point of view, it was relevant to me because hyperboloidal slice, when we construct it, it sort of needs to know what mass, what energy is in the center, so that it can be constructed properly. And let me elaborate on this. So this is a Penrose diagram for this paper from last year from Christian, David Shalab, and me. And what is depicting here is hyperboloidal slices of a Schwarzschild black hole. And there's two sets of slices. The ones in blue correspond to constant mean curvature slices, and the ones in red to a different type of slices, which are the ones that the way constructed with the height function approach that David and Christian usually employ. And the difference between this dashed and the solid lines is that the solid lines are not taking into account the mass of the black hole. They would be the same as the ones you would use to construct hyperboloidal slices of Minkowski. Whereas the dashed ones, those know about the mass of the black hole. That's here like mass different from 0, and here like this term has some -4m, where m corresponds or is related to the mass of the black hole or the mass of the system. And the difference, if we now concentrate on the pattern on Scri+, is that the solid lines that do not know about the mass of the system, actually, they do not really end up at Scri+. They actually go all the way to space like infinity, even if it's so far that we cannot see properly in the diagram. Whereas the dashed lines, the ones that do know about the mass of the system, of the black hole, they reach fictional infinity at the, let's say, appropriately. So that is, and also in the minimal gauge that Rodrigo Panoso Macedo and more people use, that one also takes into account sort of like usually if you apply that to the Tucholsky equation, to what the mass content of the Kerr black hole you are considering. So that's why I was wondering in this case, okay, if I now have a neutron star and the black hole, is it enough for me to know like what is the mass, like the total mass of the system to actually construct the hyperboloidal slices? And the spoiler is yes. And while this is, of course, like just restricted to this work I've been doing here now, thinking ahead, what would happen, if I want to have a binary? How do we, like, this, I don't know the answer to that, which is like just starting to think about these things. And by the way, if there's any questions, please interrupt me at any time. So that is the motivation. That's why that was my questions, what was in my head when I started looking into this. And now let's see how this goes. So I separated the talk into parts. One of them deals with just the neutron star. How, if I want to have a neutron star, I want to put it on a hyperboloidal slice, what is at least one way of doing it. And then the second part of the talk is going to be about, okay, now we put the neutron star with the black hole together and we do an equivalent stuff. As you can see already by the bullet points on top, the second case is more complicated. Yeah, that was not surprising though. All right, so the start is like a simple, and some of you may already have done that, or you may remember that from even your undergrad or from a while ago. Let us start with like a metric suitable for describing a neutron stars on Cauchy slices, which is given the line element on the screen, and then assuming the perfect fluid. So then we can derive the T of E equations. Just putting the summary here, so to restrict as much as possible the number of equations on the screen. Right, so indeed, the rho would be the density of the medium that integrates to the mass. And indeed, by solving this equation, one just finds an expression for what would be the GRR component of the metric on top by this one. Then there's the equation for that will give us the term that goes into the GTT component, and is related indeed to the mass and to the pressure given by P. And indeed, there's then an expression for the pressure that is related to the equation for nu. And what we do is to close the system is we add a relation between the density and the pressure. In this case, I took the simplest, which is a polytropic equation of state, where I took, so the pressure is constant times rho to the some exponent. I chose this k to be 1 and this exponent to be 2, like a sensible example. And then basically by this, you express the equation of P in terms of rho, for example, and then you basically solve the equation for the mass and for rho at the same time. And then either you solve for the remaining nu quantity, or there's another way to do it, which is actually a bit simpler, but that's not the main point of this work. So if you solve for rho and m, you will get something like this. This is done numerically. For this, you assume an initial value of the central density, which is in this case just taken to be rho equals 1. And you integrate from the origin outwards until you hit a location where your density becomes 0. That corresponds to the surface of the star. And as you can see in the black line, which corresponds to the mass is 0 at the origin, then it increases, and at some point after, so outside of this, the surface radius, it indeed is constant, and indeed a neutron star behaves gravitationally speaking as a black hole outside of this horizon. Also the surface, sorry. Yeah, I mean, I said nothing new. It's just to make sure that we're all on the same footing here, and this is the beginning of the setup. Then now we already got a solution. We have our metric for our neutron star, and we want to express on a hyperboloidal slice. I'm going to describe the way of expressing it on a hyperboloidal slice that I normally use. There's other options. I chose this one because, of course, I have views of actually implementing it in the code to later evolve it. So I'm using let's say my infrastructure. So the important part is to, instead of using the usual t tilde time, which is the usual time, we change to a t time, which is a hyperboloidal one, related to the other one via height function that depends on the radial coordinate. And I am choosing for that height function one that satisfies that the slices have a constant mean curvature, meaning this k here is a constant. Now that we have the metric, we can substitute everything in here in the right-hand side, and we obtain the following expression. Here you have metric components e to the lambda, e to the nu, h, and the idea is to okay, as k is a constant, we can integrate. Well, okay, you can actually take it out of the integral. This needs to be calculated because this is 1 for a black hole, but not for neutron star inside of the surface, and this is C is an integration constant. But now isolating H prime from this expression gives us what we call the boost, which is the spatial derivative of the height function. And everything here can be calculated numerically from our solution. And now we can, plot to see how that looks. In all of the plots I'm going to show, which are basically those in the paper I'm preparing, I'm comparing in some of them to Minkowski space, and just to see how things look in that case also for constant mean curvature slices. I'm here also including in the dashed line a black hole that has the same mass as the neutron star we have just calculated. Indeed, the solution in blue solid line corresponds to the boost of the height of that we just calculated. And here in the vertical lines, this is the surface of the neutron star, and here will be the surface of the black hole, so the equivalent black hole with the same mass. Now, one relevant part of the boost is that the combination of either GTT times the height function or the height function over GRR is the quantity that actually is meant to be so always smaller than 1 within the domain, otherwise causality would not be satisfied. And indeed, plotting minus GTT times H prime in this case, we can see that indeed for all of the cases, black hole, neutron star, Minkowski, they all only asymptotically reach 1 for larger values of the radial coordinate, which is here shown on a log scale to be able to better appreciate how this quantity actually becomes 0 as we go towards the origin. The black hole is different, but it also asymptotes to 1 for large radii. And now that we have this boost function, we need to integrate it, do a few more things, but we can actually create a Penrose diagram for the slices we computed. If you consider the same neutron star and you plot Cauchy slices, it's going to look like the diagram on the left, in which case Minkowski and neutron star slices look exactly the same. So I'm pretty sure the calculation was so I did the whole calculation. They actually just happen to coincide. Which I think makes sense for that. But the thing is, if you look at the right Penrose diagram, there the Minkowski slices and the neutron star slices do look different. And the blue ones, the neutron star ones, actually look a little kinky around the dashed line, which corresponds to the surface of the star. And that is because we're constructing the tortoise-like coordinate to make the diagram. It was having a kink there, but I think that is just the way the initial data are set in. It's just because while the density is continuous, I mean, I think it's not properly differentiable at the location of the surface of the star. And the final ingredient that, from my perspective, is needed to have initial data for a simulation is to now compactify these hyperboloidal slices that have been calculated. And the way, again, I'm used to doing is by introducing a compactification factor, which is this omega bar here. And I set it, so to determine it numerically, I impose that the gamma R component of the metric is conformally flat. Which amounts to solving this equation where we have the boost, we have our different metric components. And if you solve this numerically, you are going to get the solid blue line in this diagram here. Again, I'm comparing with Minkowski in black and with a black hole in dashed blue. In the black hole case, this corresponds to a trumpet slice. That is why, so the origin in the black hole case corresponds to actually the location of the trumpet, whereas in the neutron star case and the Minkowski case, it's the origin of the coordinate system. And again, you can also see, I hope barely see here is the surface of the star. And for a black hole with the same mass, its horizon would be here. And this is the construction for the neutron star. If there's any questions, maybe I should take them now before I go on to the next bit.
I actually have a question. Can you go back to the Penrose diagram?
Yes.
The right diagram, it seems that inside the neutron star, the curvature, the mean extrinsic curvature becomes rather large. I mean, the blue line goes up. That indicates that they are, in some sense, closer to becoming null, which means the curvature goes up. Why is that?
So when you mean the curvature,
The mean extrinsic curvature, like when the slice in the Penrose diagram goes up, I think the curvature goes up.
Okay, but we're talking about like
the extrinsic curvature, not the intrinsic one.
yes.
Embedding.
So that would be, for example, one of the components of the AIJ, I guess, if you have in mind the BSN type equations. I say it because so the trace of the extrinsic curvature is meant to be constant everywhere. That's the way the slices are constructed. Indeed. So I was actually plotting.
Yeah, sorry. Yeah, I'm just wondering, the black one inside the dashed area goes up to the blue one, and this going up seems rather steep to me. And that's what I'm wondering.
Alex, can you point with your mouse to one of the regions so that I know what Anil is talking about?
Yeah, so if I understand correctly, Anil, you're referring to this part here, like the difference between the Minkowski one and so I am not sure. So in this setup, it's because I'm in my head, I always visualize this as the metric components I normally evolve. And I can tell you for those, so in this case, the trace of the extrinsic curvature is going to be -3 everywhere. I took a relatively large value so that things would look better in the neutron star plus black hole case. But that is taken to be -3. Normally, I would actually use -1. But and indeed, if it was a smaller value, this would not look as steep. So maybe it's the choice.
Maybe it's an artifact of the embedding, like because this is not actually Minkowski.
Could be. Okay. I mean, I guess you would still. I guess you would still use like the same construction for Minkowski for the neutron star, I suppose, because the origin is regular. Okay. Well, I mean, I would have to think about more about the interpretation, because basically I do the plots, they seemed reasonable, so I did not actually think about it. But thanks for the question. I think I'll have a think.
Thank you.
So if there's no other questions or curiosities at this stage, I will continue with the next bit. So now, in order to now construct a space-time, a spherically symmetric space-time with a neutron star and a black hole at the center, so it stays spherically symmetric. These are the main steps. So the first one is already done. We already constructed the neutron star, in this case via a polytropic equation of state. And then, in order to follow the same procedure as in the paper I mentioned at the beginning, the addition so the putting together the neutron star, the black hole, is done by expressing them in isotropic form, and basically adding the conformal factors. I will give that in the expression in a moment. Then, of course, this superposition itself is not a solution of the Einstein equations, namely not for the Hamiltonian equation, so that one needs to be solved. Once the solution is found, then we will what I call hyperboloidalize, which is a new word we made up, which consists actually of expressing it on a hyperboloidal slice. And for that, there's going to be an intermediate step, which is like going from the isotropic coordinates to the aerial radius type coordinate, radial coordinate, and then finally compactify. So basically following the same steps as before, but it's going to be a few more intermediate ones. So, all right, we already had our neutron star, and now we want to, as I mentioned, add the contributions of both neutron star and black hole in this form, where this psi would be the conformal factor you would write in the metric in this way. So it multiplies to the whole spatial part. This psi in neutron star, that can be obtained from the line element we calculated before, just numerically. For the black hole, if you recall, if you take the Schwarzschild solution and write it in isotropic coordinates, you will see that you write it, well, there's going to be some part here, but then you will basically write it like this, where this psi is 1 plus mass of the black hole over 2r. And indeed, it is by using these isotropic coordinates that if you then think, so thinking about Brill-Lindquist initial data, you're basically solving the Laplacian. In the case of vacuum, you can add as many black holes as you want in this form, because the equation is indeed linear. But now we're just going to have one neutron star and one black hole. And as let's say the 1 plus m over 2r is already included, so to say, in the psi of the neutron star, for the black hole, we will just consider the part that includes the mass. And indeed, this delta here is the solution that we will solve the Hamiltonian constraint for. This is I'm just reproducing what the paper is doing, just as main steps. And right, so okay, so before actually showing you the Hamiltonian equation, this is how it looks if you add the conformal factors and you actually plot them. I'm plotting chi, which is psi to the -4. I just like the fact that it goes to the origin. Again, so if you just have the black hole, and this black hole has a mass which is 1/3 of the mass of the neutron star, so it's a rather chunky black hole. It looks like the dashed blue line. If you consider just the neutron star we calculated before, it will look like the solid line. Indeed, okay, as we will now see in the next plot, because this one is in log plot in the radial coordinate, it's easier to see that indeed the neutron star never goes to 0 because everything is finite there, whereas the black hole and the superposition of neutron star and black hole go to 0 because there's a singularity there. Yeah, so this is just the same plot. I put it in both ways to actually show the way it looks. And of course, they all asymptote to 1 for larger values of the radii. So this is the superposition. We want to now solve for the correction that satisfies Hamiltonian constraint. And before that, just wanted to say a comment on the choices of the black hole, the masses for the black hole. The paper by Richards, Baumgarten, and Shapiro that I mentioned at the beginning, and that motivated this work, they use very small black holes. Again, for bond accretion, you want a small black hole that accretes the neutron star. In my case, I'm more interested in the construction of the initial data for hyperboloidal slices. So having a bigger black hole actually helps to visualize and to see things more clearly and to calculate things. So if there's a mistake, you will see it much faster. And something that I noticed is that first thing, of course, when setting, okay, how do I decide the mass of the big black hole I want to have? Of course, you may want that the Schwarzschild radius of the black hole is going to be inside of the neutron star. Otherwise, you basically just have a very big black hole. And something like, for example, as big as the mass, actually 1.5 masses, neutron star masses for the mass of the black hole would actually already give you something whose Schwarzschild radius is inside of the neutron star. But for example, if you look now at the right plot where the mass of the black hole considered is the same as the neutron star, and here you're seeing the mass of the black hole in the yellow line, the mass of the neutron star, that was the same on both plots. In green, the just exact superposition, one plus the other, is in red. And then in blue, that's the relevant part, I calculated the Misner-Sharp mass of the addition of the conformal factors I just showed before. So for this, assuming this value of the conformal factor, you calculate the Misner-Sharp mass, which again does not satisfy the Einstein equations, but it's actually not that far away from the solution. And something, if you notice here, so from 0.08 onwards, it's always monotonically increasing, but towards the origin, it also increases, which is something which I thought was a bit of a weird behavior. And indeed, when I used such a big value of a mass of the black hole and tried to do some calculations afterwards, things were going bad inside of the horizon. So for the moment, as I thought that non-monotonically increase in Misner-Sharp mass may not be such a good idea, I restricted to a value of a black hole which is still big enough, 1/3 of the neutron star mass, but in this case it is monotonically increasing, as we can see on the diagram on the left. So unless I say otherwise, the calculations here were performed with a mass of the black hole which is 1/3 of the mass of the neutron star, so it's still quite big. That said,
I
let's
think
now.
Eric has a question,
Yes.
Alex.
Oh, yes, please go ahead, please.
What does it mean physically that the Meissner-Sharp mass is decreasing as you go outward? Does this violate an energy condition?
Well, actually, I didn't really have a thing. In any case, all that should be inside of the horizon. So I'm not sure. So in that case, I'm not sure how bad it would actually be. But I
it
didn't
would not
actually
be stationary, right? It would be completely time dependent anyway.
Because it's inside.
Yes.
Right.
Okay. Yeah. No, I can live with that inside. That's probably much weirder than I think anyway. Thank you.
Yeah. So yes. I mean, I didn't stop to actually think about the interpretation. No, thank you. Thank you for the comment. Okay, so then let's look at I will just sketch the way that it's set up to solve it in the paper in the same way I did it. The equation to solve is actually, so the Hamiltonian constraint expressed in terms of psi. And as this is not in vacuum, there's a term here at the right-hand side that depends on the density. And there's a freedom to actually use a conformal rescaling of the density, which is this psi to the m, and that is very useful because the presence of the black hole introduces a singularity at the origin, which actually messes things up quite badly if we do not choose an m, which is convenient. So for this equation, we know that of course the conformal factor for the neutron star has to be equal to the constants of the neutron star with the neutron star density. The Laplacian of the black hole conformal factor has to be 0 because it's vacuum. And we are going to set this conformally rescaled omega bar to be this expression. So the quantities for the neutron star case. And putting it all together, the first equation becomes the one before last. And this is what we solve now in spherical symmetry. It's the last equation, and we set m to be equals to -6, so that the divergent given by this m over 2r here actually goes down to the denominator and actually becomes harmless there. And in order to solve this, the condition is I solve that actually inside of the neutron star surface, because outside the solution is just the addition plus the form of the correction delta psi has to go like a over r, because that's the only possible solution outside of the surface. So by using this, we can solve the first thing I'll show, because it's a numerical relativity talk, a convergence plot. It's actually just I mean, it's a convergence plot, but one has to be taking into account most of the solutions I was using ND-solve. So there's numerical data in here that was not, whose error I don't really know so well, but when I solved with a Runge-Kutta for the previous equation, just changing the resolution in the appropriate way, I did get convergence as expected. So, I mean, that gives me, okay, things seems to be all right. And now, but more interestingly, let's look at the solution, the way the solutions look. So these are very small black holes, comparable to the ones in the paper. And what I'm plotting here is actually a log-log plot to make things more complicated, but they look actually simpler, of the negative of the correction. The correction is negative. So if you were to look at the actual correction, it goes to 0 asymptotically for larger radius, and otherwise it becomes negative and becomes like constant as you go towards the origin. And again, sorry, the smaller the black hole mass, the smaller the amplitude of the correction. That is to be expected. And to compare with results in the paper, I did so this is a plot showing the densities for small values of so m here is the mass of the black hole. On the right, sorry, is the plot I made. On the right, the one I made, on the left, the one from the paper. And indeed, this row goes to 0 at smaller values of the radial coordinate, the smaller the mass is. So it becomes, this row is non-zero for closer to the origin for smaller black hole, which makes sense because that means that the black hole is smaller. Yeah, so that is to say that solves the Hamiltonian constraint. And now we want to take our solution, which is, just to remind you, the one constructed with this conformal factor. Now we have all of the ingredients because we determined this numerically. And we want to actually hyperboloidalize it. And in order to do that, at least the way I know how to do it is by having the metric expressed with an aerial type radius, not in an isotropic form. So it made sense to me to actually undo this transformation. Now, the difficulty is that if you have a black hole, the value of GRR, well, actually, and also like for GTT, changes sign as well. Okay, changes sign, yeah, at the horizon. So actually that one diverges, but 1/8 is fine. And that posed a problem because, okay, something else is that now just thinking, sorry, this is a bit more technical. For me, it took me a while to actually understand how to at least use this for my solution. If you think about just a black hole in isotropic coordinates, where isotropic coordinates are given by the barred quantity, by the barred r, whereas r tilde would be the Schwarzschild radial coordinate. Here we are plotting the Schwarzschild coordinate on the x-axis and the isotropic one on the y-axis. Outside of the horizon, where this expression is actually valid as such, the isotropic coordinate actually maps twice to the Schwarzschild one. For smaller values than 1/2, so I'm assuming that m is 1 for this specific plot. For smaller values that r, it just basically maps from r Schwarzschild 2 to the infinite, and for larger values as well. And that's basically because you're actually assuming that GTT is positive outside of the horizon. If you want to look at the solution inside of the horizon, then actually this derivation is no longer valid. But I was actually having trouble to understand how to solve it inside of the horizon. So what I came up with, and I'd be more than happy to actually have all the ideas of ways to actually do this better, would be if you actually solve this equation for r bar, the isotropic radial coordinate, in terms of the Schwarzschild one, you actually realize this, the real solution, which is the one I was talking about, the solid lines, but you can also see that there is an imaginary solution, complex solution, which is given by the dashed lines. And actually in that one, you can actually feed in data for r that will give you values of r tilde. Of course, if you do everything in closed form, as all the expressions make sense, even if you just do the calculation for assuming that GRR is positive and everything is outside of the horizon, the equations will actually be valid anywhere because you just substitute in closed form expressions. But if you try to think numerically, it becomes more complicated because, again, the solution, the superposition solution, we only have that numerically. So I will not go into more details, just to say that this was a bit of a tricky thing to do. What I ended up doing was to calculate the complex part of the solution for my apologies, for the black hole, for the Misner-Sharp masses that I was assuming, I was getting for the whole solution, and then finish this transformation from the isotropic radial coordinate to the Schwarzschild type one, like aerial type one. But yeah, maybe if there's any questions or any comments or any recommendations, we can go back to this at the end. Once that is done, then one can indeed calculate GRR, in this case, one of GRR, so it's easier to look at in the plot. Here we are looking at it with our Schwarzschild or aerial type radial coordinate in log scale. I'm just including the Minkowski, it's just one, just for reference. If we had just a black hole with the mass of the mass which is 1/3 of the neutron star mass, we would be having the dashed line, and its horizon is here with this the dot dashed line in blue. If we just had the neutron star, we would be having the solid blue line, which has a perturbation because there's the neutron star, but then that goes away as we go towards the origin. And for the interesting case, which is the one we actually after, the black dashed line, it is very close to the neutron star, but at some point it becomes different. And actually, I said something wrong, which is this. I just remembered for this plot, the mass of the black hole is actually smaller because the black hole radii are closer to the origin. The next slide will actually show the difference. And in this case, the location of the surface of the neutron star is given by this line over here. Now let us compare. Sorry about the what I missaid before. What we just saw is now on the left. On the right, there's the case where the mass of the black hole is bigger, is 1/3 of the neutron star mass. And in this case, indeed, the solution, the dashed black line, is closer to the neutron star solution for less, because then the effect of the black hole, the mass of the black hole, sort of has its effect at the larger values of the radii, and now the location of the horizon of the superposition of neutron star plus black hole is outside, like it's larger than 0.1, whereas before it was clearly smaller than 0.1. So this is the reconstruction in terms of the areal radius of the superposition. And again, as I mentioned, we did that because now we're going to hyperboloidalize this. And for that, we determine the boost. And here we're just dealing with the spatial part of the metric. But in order to construct the boost, we also need to assume what is, let's say, our GTT. And in this case, I made a choice to assume that the GTT is just -1 over GRR, which is the case where that happens usually for a black hole. And that is also convenient because it makes the calculation of the boost function simpler. Namely, you can calculate the boost by this form, where KCMC and CCMC are constants. F of R is basically what we just saw before. This dashed line, the black dashed line, that is F of R. So you plug this in, you can calculate H numerically. KCMC we set. CCMC has to be tuned if we want to actually have a trumpet solution and not different slices that may actually go into a singularity, or slices that do not exist that become complex for part of the domain. If we choose CCMC in the right way, that will give us a trumpet slice that goes all the way into the black hole and towards never actually going towards a singularity but never actually reaching it. Yeah, so that was a choice I made, and I'm skipping the details. There's a lot of stuff behind this Penrose diagram. It looks like a normal black hole Penrose diagram, but it's a lot of work behind it. But this corresponds to the superposed solution neutron star plus a black hole with a mass 1/3 of the neutron star plus the correction to satisfy the Hamiltonian constraint. And again, the solid lines correspond to hyperboloidal slices, and they are trumpet slices because they go all of the way here without going into the singularity. And if you can barely see here towards the right, a dashed line, that actually corresponds to the location of the surface of the neutron star. So everything we're seeing pretty much is inside of the neutron star. I tried to make the Penrose diagram bigger. That's why I also put a big mass for the black hole to see if that would look a bit clearer. But that's all I could do, again, using the common ingredients, the common way of actually creating the Penrose diagram. Maybe that can be improved for this. And yeah, so these are the slices. And now finally, for the code to be able to implement this in the code, we need to compactify it. And if you actually did I skipped one. Well, this is calculated as before, as imposing that the spatial metric be conformally flat because we're in spherical symmetry. And in this case, there's many lines here. The relevant one is the thick dashed black line. that corresponds to the superposition with correction. It is indeed something in between the solid blue line, which is the neutron star conformal factor, and the blue dashed one, that is just a single black hole with 1/3 of the mass of the neutron star. Indeed, the black one is in between both, but then goes to 0. Because there's a black hole present, a singularity present, and if we look at that with log scale in the x-axis, indeed we can clearly see the dependence. And also I'm plotting here. Here in black is the location in terms of the compactified radial coordinate of the horizon of the superposition, and here in black would be the surface of the neutron star. And okay, so that's basically the contents of what I've been working on. And the next step will be to actually express my initial data in terms of this. This is a work in progress, so there's not even labels in this plot, but I'll tell you what it is. This is the labs. This is the conformally rescaled labs that we would actually give us initial data for the simulation. In blue is the usual Minkowski slice I use. In green, that's the neutron star one. So if I wanted to evolve the neutron star, I would be giving this green line. Oh, sorry. Then the yellow one, that's just a single black hole, but the red one, that's the superposition. If you see, it's close to the green one at larger radii, and it goes to the origin, same as the yellow one at the origin, denoting that this is the location of the puncture of the trumpet, the location of the trumpet. And if you do this for the labs, for the shift, for the one term of the extrinsic curvature, as Anil was mentioning before, and for the conformal factor, everything else is either 1 or 0 in this setup. So that means basically you can just evolve that, And so I would just like to wrap up. Actually, haven't been checking the time. I don't know how I'm doing. Oh, that's enough time for questions. So that is. So this is a project I actually started because I was really curious to see how that would go. And at least I'm happy that now I think, oh, this was so easy, but I mean, it's easier once you've already done it. And so for the future, the main thing for this is initial data. The idea will be to evolve it in spherical symmetry. The challenging part will be to actually also include the relativistic Euler equations in the hyperboloidal setup. That's not, I mean, that's something I still need to look into. I have not spent any time on that, but I'm excited to do that. And that would allow us to evolve the neutron star initial data, perturbing those initial data as well. And indeed carry out the main idea behind this project, which is indeed boundary accretion by giving us initial data, the neutron star plus small black hole that I also showed before. And now thinking about like longer term plans for the future beyond spherical symmetry, I would be very interesting to see how, if there's a possibility to do a similar type of construction for hyperboloidalizing a space-time, and now thinking about the two objects not being both centered at the origin, but as a binary or as let's say not in the same location, how because in absence of symmetry, now I was calculating the Misner sharp mass to see, okay, how does this look? You cannot do this in the general case. So how do we, if we do need to know exactly what's in the system to construct the hyperboloidal slices, how can we do that? So it's a question it's not clear to me in any case. And well, you may notice here I wrote in red, evolve 3D perturbed neutron stars. Well, we need to have the 3D hyperboloidal evolution working properly, plus the relativistic Euler equations, which is something which is planned and it is going to happen, but I mean, not just right yet. And with all that said, hope I was not too confusing. I would like to thank you for your attention and see if there's any more questions I could answer. Thank you.
Thanks, Alex.